Good morning. My name is Manikan. Now I'm going to say about supersonic inlet noise related to the course of aerospace propulsions. Supersonic inlets, depending upon the flight speed and the mass flow demanded by the engine, the inlet may have to operate with wide range of incident stream conditions. So these are the two stream conditions, that is subsonic intake and supersonic intake. This is a picture 1 and this is a picture 2. The point 1 and point 2 for these pictures, and see this here. This is a diagrammatical representation of mass flow and other things, and a pressure distribution here, and this is a velocity distribution. For this, at one, it's varying from 1 to 2. Here also from 1 to 2. So see here, this subsonic intake. This velocity is having some convergent thing with respect to the p. And see here, it is having some convergent thing. So let us discuss about that one. So the figure 2 shows that the performance of supersonic intake during two typical supersonic conditions, namely takeoff and cruise. So u1 less than u infinity, and p1 greater than p infinity, and p01 is equal to p0 infinity, and t01 is equal to t0 infinity. During low speed high thrust operations, the figure 2b, the same engine will have to demand more mass flow and the upstage stream. The intake will be accelerated. The stream tube will have a converging shape, and the following conditions will be satisfied then. So for high speed and cruise conditions, the stream tube will have divergent shape, and following conditions can be stated, such as u1 less than u infinity, and p1 greater than p infinity, and p0 1 is equal to p0 infinity, and t01 is equal to t0 infinity. For both cases, the takeoff and cruise, there will be initial diffusion within the intake up to engine phase. The static pressure will rise and the air speed will be reduced. The total pressure will be also decrease due to the screen friction, while the total temperature will remain unchanged as the flow through the diffuser is adiabatic. Thus, for both takeoff and cruise conditions will be same. So these are the performance parameters. Since the inlet speed of the engine should be nearly constant for different operating conditions, then if this pressure increases too large, the diffuser may stall due to the boundary layer separation. The stalling usually reduces the stagnation pressure of the stream as a whole. That is, P2 by P1 takeoff is greater than P2 by P1 cruise. Isentropic efficiency, ND, the isentropic efficiency is given as H02S minus HA by H02 minus HA. And the stagnation pressure ratio is RD. Isentropic efficiency is ND. It is defined as the ratio of ideal to actual enthalpy change during the diffusion process. So see this is the RD, the stagnation pressure ratio. Stagnation pressure ratio is defined as the ratio between the average total pressure of the air entering to the engine to the free stream air. So that is RD is equal to P02 by P0 infinity. So it says that the average total pressure of the air entering to the engine to that of the free stream air.